Right now, as you settle in for the night, most of the universe remains invisible to you and to every telescope ever built. It is not hiding behind anything. It is simply made of something your eyes were never designed to see. The stars you know, the planets you have learned about, the galaxies stretching across the heavens, all of it amounts to less than 5% of everything that exists. The rest is darkness, and that darkness has a name. Tonight, we explore dark matter and dark energy, the twin mysteries that make up nearly 95% of the cosmos. They do not shine, they do not reflect. They simply are, shaping everything we see while remaining forever out of sight, like a vast and patient presence holding the universe together. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will carry you through the invisible architecture of existence. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever wondered what lies in the spaces between the stars, in the emptiness that is not quite empty? You are not alone. If this journey brings you comfort, consider subscribing, sharing with a friend who needs rest, or simply returning whenever sleep feels far away. Take a slow breath now and feel your body begin to settle. Let the tension in your shoulders ease. Let the weight of the day begin to fade. Tonight, we wander through the unseen together, where the darkness is not frightening, but simply waiting to be understood. Let us begin. Dark matter makes up about 27% of the universe. If you could somehow weigh everything in the cosmos, the stars and planets and galaxies you see in photographs would account for less than 5% of the total mass, and the vast majority of what remains is something called dark matter, a substance that neither shines nor reflects nor absorbs any form of light, yet exerts a gravitational pull so powerful that it shapes the entire structure of the universe. Scientists estimate that dark matter accounts for roughly 27% of everything that exists, meaning there is more than 5 times as much dark matter as ordinary matter. The atoms and molecules that make up your body, the air you breathe, and every object you have ever touched or seen. It is everywhere, yet it passes through the world unnoticed. You have lived your entire life surrounded by something you cannot see. Dark matter does not emit, absorb, or reflect any light. The reason dark matter remains invisible is not because it hides behind other objects or lurks in distant corners of space, but because it simply does not interact with light in any way, not emitting photons like a star, not absorbing them like a dust cloud, not reflecting them like a planet or moon, leaving astronomers with no direct way to photograph or observe it using any telescope ever built. Light passes through dark matter as though it were not there, which in practical terms means that even if a dense clump of dark matter were floating right in front of your eyes, you would see only darkness, the stars behind it shining through without disturbance. This is what makes dark matter so strange and so difficult to study. It is detectable only through its gravitational effects. Darkness defined not by shadow, but by utter transparency. The existence of dark matter was first suggested in the 1930s. The story of dark matter began nearly a century ago, when astronomers first noticed that the universe did not seem to add up, that galaxies and clusters of galaxies were behaving as though they contained far more mass than anyone could see with telescopes. In the early 1930s, scientists studying the movements of galaxies within clusters realized that the visible stars alone could not account for the gravitational forces holding everything together, and they began to suspect that something invisible was contributing additional mass, something that did not glow or reflect any light. At the time, this idea was met with skepticism, and many physicists hoped that better observations or revised theories would eventually explain away the discrepancy. But the mystery only deepened. Nearly a century later, dark matter remains as elusive as ever. Swiss astronomer Fritz Zwicky noticed galaxies moving too fast for their visible mass. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of over 1,000 galaxies bound together by gravity, when he noticed something deeply puzzling about the way these galaxies were moving through space. By measuring the velocities of individual galaxies within the cluster, Zwicky calculated how much mass would be needed to hold them all together, and found that the visible matter, all the stars and gas he could see, accounted for only a tiny fraction of the required total. He called the missing substance Dunkelmaterei, which translates from German as dark matter, and proposed that vast quantities of invisible material must be scattered throughout the cluster. His colleagues largely dismissed the idea as speculation. History would prove him remarkably prescient. Vera Rubin confirmed dark matter through her study of galaxy rotation curves. Decades after Zwicky's initial observations, an American astronomer named Vera Rubin provided some of the most compelling evidence for the existence of dark matter through her meticulous study of how galaxies spin. Working in the 1960s and 70s, Rubin measured the speeds at which stars orbit around the centers of spiral galaxies, expecting to find that stars farther from the center would move more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. Instead, she discovered that stars at the edges of galaxies were moving just as fast as those near the center, which was only possible if enormous amounts of invisible mass surrounded each galaxy like an unseen halo. Her work transformed dark matter from fringe hypothesis to scientific consensus. Rubin spent her career illuminating what could not be seen. Galaxies spin so fast they should fly apart without dark matter holding them together. When astronomers measure how quickly spiral galaxies rotate, they find speeds that seem impossible given the amount of visible matter present, with stars at the edges spinning so fast that they should be flung outward into intergalactic space, like water flying off a spinning wheel, if only gravity from the visible stars were holding them in place. The fact that galaxies remain intact, holding their graceful spiral shapes over billions of years, tells us that something else must be providing additional gravitational attraction, an invisible mass that wraps around each galaxy and binds its stars together despite their tremendous speeds. Without dark matter, galaxies as we know them could not exist, and the elegant pinwheels of light scattered across the cosmos would have dispersed long ago into lonely drifting stars. Dark matter is the unseen hand that keeps the cosmic dance from falling apart. Dark matter creates gravitational lenses that bend light from distant galaxies. One of the most beautiful ways that dark matter reveals its presence is through a phenomenon called gravitational lensing, in which the immense mass of dark matter bends the fabric of space itself, causing light from distant galaxies to curve around it like water flowing around a stone in a stream. When astronomers observe a massive cluster of galaxies, they often see the images of galaxies behind the cluster stretched, smeared, and sometimes multiplied into arcs and rings, distorted by the gravitational influence of dark matter concentrated in the foreground. By carefully analyzing these distortions, scientists can map the distribution of dark matter in clusters, creating detailed pictures of something that emits no light at all. Gravitational lensing has become one of the most powerful tools for studying the invisible universe. The darkness bends light the way wind bends tall grass. The Bullet Cluster provides some of the strongest evidence for dark matter. About 3.8 billion light-years from Earth, two enormous clusters of galaxies collided and passed through each other, in an event that has given scientists one of the clearest demonstrations that dark matter is real and distinct from ordinary matter. As the clusters merged, the hot gas that makes up most of the visible matter in each cluster slowed down and got left behind due to friction, while the galaxies themselves, too far apart to physically collide, continued moving through largely unimpeded. When astronomers mapped the gravitational field of the resulting bullet cluster using gravitational lensing, they found that most of the mass had moved forward with the galaxies, separated from the hot gas left behind. This separation proves that the majority of mass in the cluster is not the gas, but something invisible. The bullet cluster is a cosmic collision frozen in time. Dark matter likely consists of particles that have never been detected. Despite decades of searching, scientists have not yet been able to identify exactly what dark matter is made of, though most believe it consists of a new type of subatomic particle, something beyond the catalog of known particles described by the Standard Model of Physics, something that interacts with ordinary matter only through gravity and perhaps the weak nuclear force. These hypothetical particles would have been created in the extreme conditions of the early universe, and they would still be drifting through space today in enormous quantities, passing through planets and stars and galaxies without ever being noticed. The search for dark matter particles has become one of the great quests of modern physics, driving experiments deep underground and to the edges of detection technology. We know dark matter exists by what it does, but we still do not know what it is made of. WIMPs are one of the leading candidates for dark matter particles. Among the many theoretical particles that could explain what dark matter is made of, one of the leading candidates is something called a WIMP, which stands for Weakly Interacting Massive Particle, a hypothetical particle that would be heavy enough to exert gravitational influence, but would interact with ordinary matter so rarely that it could pass through the entire Earth without ever hitting a single atom. WIMPs are attractive to physicists because they arise naturally in certain extensions of the Standard Model, and because the predicted amount of WIMPs produced in the early universe matches the observed amount of dark matter remarkably well, a coincidence often called the WIMP miracle. However, despite decades of increasingly sensitive experiments designed to detect WIMPs, no conclusive evidence has yet been found, leading some scientists to question whether WIMPs exist at all. The miracle may yet prove to be a mirage. Axions are another theoretical particle that could explain dark matter. Beyond WIMPs, another leading candidate for dark matter particles is the axion, a hypothetical particle originally proposed in the 1970s not to explain dark matter, but to solve a completely different problem in particle physics, one involving the strong nuclear force that holds atomic nuclei together. Axions, if they exist, would be extraordinarily light, perhaps 1 trillion times lighter than an electron, and would interact with ordinary matter so weakly that detecting them requires entirely different experimental techniques than those used to hunt for WIMPs. Several experiments around the world are now searching for axions by attempting to convert them into detectable photons using powerful magnetic fields, turning invisible particles into flashes of light that might be caught by the most sensitive instruments ever built. The axion remains theoretical but not impossible. Sometimes the answer hides in what we were not originally looking for. Dark matter particles pass through ordinary matter without interacting. Whatever dark matter is made of, its defining characteristic is that it almost never interacts with normal atoms, passing through solid rock and metal and flesh as though they were not there, which is why dark matter is so extraordinarily difficult to detect despite being all around us. If you could shrink down to the size of an atom and watch dark matter particles streaming through your body, You would see them pass by without ever touching you, traveling in straight lines through the spaces between your atoms, through the nuclei themselves, continuing on their paths through the earth below and the air above without stopping. The chances of a dark matter particle actually colliding with an atom are so vanishingly small that even trillions of particles passing through a detector might produce only a handful of detectable events over the course of years. Dark matter lives alongside us in perfect isolation. Billions of dark matter particles may be passing through your body every second. Right now, as you lie here listening to these words, streams of dark matter particles are flowing through your body continuously, billions upon billions of them passing through the room, through your bed, through your skin and bones and organs without leaving any trace whatsoever, like ghosts drifting through walls in stories, except that these ghosts are real and permeate the entire universe. Scientists calculate that the average density of dark matter in our region of the Milky Way means that roughly 1 billion dark matter particles pass through every square meter of your body each second, a river of invisible particles flowing through you exactly as it flows through the earth beneath and the stars above. You cannot feel them because they do not interact with the atoms in your nerves. You are bathed in darkness constantly and have never once noticed. Deep underground laboratories search for rare dark matter collisions. Because dark matter particles interact so rarely with ordinary matter, scientists hoping to detect them must shield their experiments from every possible source of interference, including the constant rain of cosmic rays that bombards the Earth's surface from outer space. And the solution they have found is to go underground, building laboratories in mines and tunnels beneath kilometers of solid rock that can block all but the most penetrating radiation. In these subterranean sanctuaries, physicists operate detectors made of the purest materials available, waiting patiently for the rare moment when a dark matter particle might happen to collide with an atomic nucleus, producing a tiny flash of light or a minute vibration that could be distinguished from the background noise. Years pass between potential detections. The hunt for dark matter is a lesson in patience, in waiting beneath mountains of stone for the faintest contact with the invisible. The Large Hadron Collider has attempted to create dark matter particles. While some experiments search for dark matter particles drifting through space, others have tried to create them from scratch by smashing ordinary particles together at extreme energies in particle accelerators like the Large Hadron Collider, the enormous underground ring beneath the border of France and Switzerland that is the most powerful accelerator ever built. When protons collide at nearly the speed of light within the LHC, the energy released can transform into mass, potentially creating new particles that have never been observed before, and physicists have carefully analyzed the debris from trillions of these collisions, looking for signs that dark matter particles might have been produced. So far, no definitive evidence has emerged, but the search continues as the LHC increases its power and sensitivity. Creating darkness from light remains one of the great ambitions of modern physics. And as you rest here, surrounded by the invisible, there is nothing you need to understand completely. Let these mysteries wash over you like a slow tide. Take a breath and feel your body grow heavier, more at peace with the unknown. Dark matter forms a vast cosmic web stretching across the universe. On the largest scales, dark matter is not distributed evenly throughout the cosmos, but instead forms a vast three-dimensional web, with long filaments of dark matter stretching across hundreds of millions of light years, connecting nodes where dark matter concentrates into dense clumps and leaving enormous voids in between where almost nothing exists. This cosmic web is the underlying architecture of the universe, the scaffolding upon which all visible structures are built, with galaxies and clusters of galaxies forming along the dark matter filaments like beads of dew gathering on a spider's web at dawn, and the great empty voids between filaments growing ever larger as the universe expands. If you could see dark matter, you would see not empty space scattered with galaxies, but a vast interconnected structure holding everything in place. The universe is a web woven from darkness. Galaxies cluster along the filaments of this invisible web. When astronomers map the positions of millions of galaxies across the sky, they find that galaxies are not scattered randomly through space, but instead cluster along particular lines and sheets, forming patterns that trace the underlying distribution of dark matter in the cosmic web, drawn together by gravity into the densest regions where dark matter has accumulated over billions of years. The visible galaxies are like lanterns hung along the cables of a suspension bridge, revealing the structure of something much larger and more fundamental beneath them, something that cannot be seen directly but whose presence is betrayed by the lights it attracts. Where dark matter concentrates, gravity pulls ordinary matter in, and stars eventually begin to shine. Where dark matter is sparse, the void stretches empty for millions of light years. Light follows darkness across the cosmos. The spaces between filaments are called cosmic voids. Between the filaments of the cosmic web lie vast regions called cosmic voids, enormous bubbles of nearly empty space that can span hundreds of millions of light years across, containing almost no galaxies, very little ordinary matter, and presumably far less dark matter than the surrounding filaments and nodes. These voids are not completely empty, as some lonely galaxies do drift through them, but they are the emptiest places in the known universe, regions where gravity has gradually pulled matter outward toward the denser filaments, leaving behind stretches of space that have become increasingly sparse over cosmic time. If you could travel through a cosmic void, you would see almost nothing, not even the faint glow of distant galaxies, just darkness stretching in every direction for distances the human mind struggles to comprehend. The voids are the spaces between the threads of reality. Our own Milky Way is surrounded by a massive halo of dark matter. The Milky Way galaxy, our home in the cosmos, is embedded within an enormous spherical halo of dark matter, extending far beyond the visible stars and gas that make up the spiral disk, a dark cloud of invisible particles engulfing everything from the central bulge to the outermost dwarf galaxies orbiting around us. Scientists estimate this dark matter halo contains perhaps 10 times more mass than all the visible matter in the Milky Way combined, a reservoir of invisible substance providing most of the gravitational attraction holding our galaxy together and determining how it moves through space. You have spent your entire life within this halo, orbiting the galactic center with the sun and every star you have ever seen. We live inside a shell of darkness we have only recently begun to understand. The dark matter halo around the Milky Way extends far beyond the visible stars. While the visible disk of the Milky Way stretches about 100,000 light-years across, the dark matter halo surrounding it is much larger, extending outward to perhaps 300,000 light-years or more. A vast, invisible sphere containing not only our galaxy, but also dozens of smaller satellite galaxies orbiting around us. The edge of the dark matter halo is difficult to define because dark matter has no sharp boundary but gradually thins as you move farther from the galactic center, fading into the sparser dark matter between the Milky Way and neighboring galaxies. Some satellite galaxies drifting through this halo are themselves almost entirely dark matter, containing so few stars that they are nearly invisible. The true extent of our galaxy is drawn in darkness rather than light. And from the invisible halo surrounding our galaxy, we now turn to the nature of dark matter itself. and the strange ways it refuses to behave like anything we know. Dark matter does not interact with the electromagnetic force. The reason dark matter neither emits nor absorbs light is that it does not participate in the electromagnetic force, the fundamental interaction responsible for all light and color in the universe, for how atoms bond into molecules, for the solidity of matter and the glow of stars. Ordinary matter interacts electromagnetically because it carries electric charge, but dark matter appears to carry no charge at all, making it immune to electromagnetic effects, unable to be pushed or pulled by magnetic fields, unable to emit or absorb photons, utterly invisible to any detector that relies on light. This is why dark matter can pass through ordinary matter without disturbing it, as there is no force that would cause them to affect one another except gravity. Dark matter exists in perfect electromagnetic silence. Dark matter clumps together through gravity alone. Even though dark matter does not interact with light or the electromagnetic force, it still feels the pull of gravity just like ordinary matter. And this gravitational attraction causes dark matter to slowly clump together over cosmic time, gathering into denser regions where its collective mass exerts an even stronger gravitational pull, drawing in more dark matter and eventually ordinary matter as well. In the early universe, when everything was spread nearly uniformly across space, tiny fluctuations in the density of dark matter began to grow, with slightly denser regions pulling in material from their surroundings and becoming denser still, until eventually the cosmic web of filaments and clusters began to take shape. Ordinary matter, feeling the gravitational pull of these dark matter concentrations, fell inward as well, eventually forming the first stars and galaxies. Dark matter sculpted the universe using only gravity. No other tool was needed. Without dark matter, galaxies would have formed much later in cosmic history. One of the most important roles dark matter plays is speeding up the formation of cosmic structures by providing gravitational wells into which ordinary matter can fall. And without it, galaxies would have formed much later in cosmic history if they formed at all. Ordinary matter in the early universe was kept smooth by pressure from radiation, unable to clump until the cosmos cooled sufficiently. But dark matter, which does not interact with radiation, could begin clumping immediately after the Big Bang, creating seeds of future structures long before ordinary matter was free to join. By the time ordinary matter could finally collapse, dark matter had already built the gravitational scaffolding. Without dark matter, the universe might still be a thin haze of gas. Structure required something invisible. Dark matter acted as scaffolding for the first structures in the universe. When cosmologists describe how the universe evolved from the smooth, nearly uniform state it was in shortly after the Big Bang to the complex web of galaxies and clusters we see today, they often speak of dark matter as the scaffolding upon which visible structures were built, the invisible framework that attracted ordinary matter into the patterns we now observe across the night sky. Because dark matter could begin clumping earlier than ordinary matter, the first concentrations of mass in the universe were made almost entirely of dark matter, dense regions that grew slowly larger and more massive over hundreds of millions of years, until ordinary matter finally fell into them and began forming the first stars. Remove the dark matter from this story, and the visible universe would never have assembled. The grandest cathedrals of light were built upon foundations of darkness. Computer simulations can model the distribution of dark matter across billions of years. To understand how dark matter shapes the universe, scientists run enormous computer simulations that track the gravitational interactions of billions of particles over cosmic time, starting from conditions similar to those just after the Big Bang, and letting the simulated universe evolve forward for billions of years to see what structures emerge. These simulations require some of the most powerful supercomputers ever built, calculating the gravitational pull between countless particles and allowing dark matter to clump and flow according to the laws of physics, producing virtual universes that can be compared against astronomical observations of the real cosmos. The results have been remarkably successful, with simulations producing cosmic webs and galaxy distributions that closely match what astronomers actually see when they survey the sky. We can create a universe inside a computer. Darkness follows the same rules whether simulated or real. These simulations produce structures remarkably similar to the observed universe. When cosmologists compare the virtual universes produced by their dark matter simulations against observations of the actual cosmos, they find an astonishing level of agreement, with simulated galaxy clusters, filaments, and voids closely matching the structures found in large-scale surveys of the real sky, suggesting that our understanding of how dark matter behaves is remarkably accurate, even though we have never directly detected a dark matter particle. The cosmic web that emerges from these simulations, with its long strands of dark matter connecting dense nodes and surrounding vast empty voids, looks very much like the cosmic web that astronomers map by tracing the positions of millions of galaxies across the heavens. This agreement gives scientists confidence that dark matter is real and that the standard model of cosmology is on the right track. Virtual darkness matches observed reality. The simulations are telling us something true. Dark matter density varies throughout space, creating peaks and valleys. The distribution of dark matter across the universe is not uniform, but instead varies from place to place, with some regions containing enormous concentrations where dark matter has accumulated over billions of years, and other regions remaining nearly empty as dark matter has drained away toward denser structures. These variations create a kind of cosmic landscape, with peaks where galaxy clusters form at the intersections of dark matter filaments, and deep valleys where the great voids stretch across space, containing almost nothing at all. The density of dark matter in any given location determines how strongly space is curved by gravity, how light bends as it passes through, and whether ordinary matter can accumulate to form stars and galaxies, or whether the region remains forever barren. We live in a particular fold of this invisible landscape. The terrain of darkness is as varied as any mountain range. The cosmic microwave background contains hints of dark matter from the early universe. The cosmic microwave background is the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and for light to travel freely through space. And this ancient glow still reaches us from every direction, carrying information about what the universe was like in its earliest epochs. Embedded in the tiny temperature variations of the cosmic microwave background are signatures of the dark matter that existed in the early universe, subtle patterns imprinted by the gravitational influence of dark matter on ordinary matter and light before they separated from each other. By carefully analyzing these patterns, cosmologists can determine how much dark matter existed in the early cosmos and how it was distributed. The oldest light carries messages about the oldest darkness. We read the past through patterns in the glow. Tiny fluctuations in the early universe seeded the dark matter structures we see today. In the very early universe, quantum fluctuations created tiny variations in density, regions that were slightly denser or slightly sparser than their surroundings by just a few parts in 100,000. And these minute variations were stretched to enormous scales during a period of rapid expansion called inflation, becoming the seeds from which all cosmic structure would eventually grow. Dark matter, responding to gravity, began to fall toward the slightly denser regions and away from the sparser ones, a process that amplified the initial variations over hundreds of millions of years, until the small wrinkles in the primordial cosmos had become the filaments and clusters and voids of the present-day cosmic web. Everything in the universe today, every galaxy and every star, traces its origin back to these quantum fluctuations, magnified by dark matter into visible reality. The largest structures grew from the smallest beginnings. Dark matter may have been created in the first fractions of a second after the Big Bang. Cosmologists believe that whatever particles make up dark matter were created in the extreme conditions of the very early universe, perhaps in the first fractions of a second after the Big Bang, when temperatures and densities were so high that particles and antiparticles were constantly being created and annihilated in a roiling sea of energy. At some point during this era, the specific processes that produced dark matter particles either stopped or slowed dramatically, leaving behind a relic population of dark matter that has persisted through all the subsequent history of the cosmos, expanding along with the universe and gradually clumping together under the influence of gravity. The exact mechanism by which dark matter was created remains unknown, hidden behind the veil of extreme physics that governed those earliest moments. Dark matter is a fossil from the birth of everything. And from the ancient origins of dark matter, we now move to something even stranger, a force pushing the universe apart rather than holding it together. Dark energy makes up about 68% of the universe. If dark matter seems strange, dark energy is stranger still and far more abundant, accounting for roughly 68% of the total energy content of the universe, more than twice as much as dark matter and more than 12 times as much as all the ordinary matter in every star and planet and living creature combined. Unlike dark matter, which clumps and concentrates and holds galaxies together, dark energy is spread uniformly throughout all of space, a mysterious property of emptiness itself that does not gather anywhere, but instead pervades everything equally, from the voids between galaxy clusters to the air in your lungs to the space between the atoms in your bones. Its influence is not to attract, but to push, to stretch the fabric of space and accelerate the expansion of the universe. Dark energy is the dominant ingredient in reality. Dark energy was discovered through observations of distant supernovae in 1998. The discovery that changed our understanding of the cosmos came in 1998, when two teams of astronomers studying distant Type Ia supernovae, the explosive deaths of certain white dwarf stars that always release roughly the same amount of light, found that these supernovae appeared dimmer than they should have been if the expansion of the universe was slowing down, as everyone expected. The only way to explain the observations was if the expansion of the universe was actually speeding up, pushed outward by some unknown force acting against the pull of gravity, a force that came to be called dark energy. This discovery shocked the scientific community, overturning decades of assumptions about how the cosmos would evolve, and it remains one of the most profound findings in the history of astronomy. We learned that the universe is running away from itself and accelerating as it goes. The expansion of the universe is accelerating, not slowing down. Ever since astronomers first discovered that the universe is expanding, with distant galaxies moving away from us in all directions, most assumed that this expansion would gradually slow down over time as gravity pulled everything back together, just as a ball thrown upward slows down before it falls. But the supernova observations of 1998 revealed the opposite, that the expansion is not slowing but accelerating, with distant galaxies receding ever faster the further back in time we look, as though some invisible force is pushing the cosmos apart more and more forcefully with each passing eon. This acceleration means that the future of the universe will be very different from what anyone expected, not a gradual collapse back toward a final crunch, but an endless expansion into ever-increasing emptiness. The universe is not falling back together. It is flying apart and speeding up as it goes. This accelerating expansion was completely unexpected by scientists. Before 1998, virtually no one in the scientific community expected to find that the expansion of the universe was accelerating, as all the theoretical models and observational data seemed to point toward a universe whose expansion was either slowing down or perhaps just barely holding steady, balanced between gravitational attraction and the momentum of the initial Big Bang. The discovery of accelerating expansion came as a profound shock, forcing physicists and cosmologists to completely rethink their understanding of the cosmos and to introduce an entirely new component of the universe, dark energy, that no one had anticipated and that remains poorly understood to this day. Science sometimes advances by confirming what we expect, but the greatest discoveries often come when nature defies our predictions. The acceleration of the universe was a surprise written in starlight. Before dark energy was discovered, most assumed gravity would slow cosmic expansion. For most of the 20th century, cosmologists debated not whether the expansion of the universe was slowing down, which nearly everyone took for granted, but rather how quickly it was slowing and whether it would eventually stop altogether or merely asymptote toward a steady state. The force of gravity, acting between all the matter in the universe, was expected to steadily decelerate the expansion that began with the Big Bang, pulling galaxies back toward each other even as they continued to drift apart, like a ball thrown upward that never quite escapes the Earth. Some thought the universe might eventually collapse in a big crunch, while others believed it would expand forever, but more and more slowly. No one expected it to speed up. The universe had other plans, written in a language we had not yet learned to read. Type Ia supernovae serve as standard candles for measuring cosmic distances. The key to discovering dark energy lay in using a special type of stellar explosion called a Type Ia supernova, which occurs when a white dwarf star in a binary system accumulates enough matter from its companion to trigger a thermonuclear explosion of consistent brightness, always releasing roughly the same amount of energy regardless of where in the universe it occurs. Because these supernovae are so uniform, astronomers can use them as standard candles, comparing their apparent brightness as seen from Earth against their known intrinsic brightness to calculate how far away they are, much as you might judge the distance to a car at night by how bright its headlights appear. By observing Type Ia supernovae in distant galaxies, scientists could measure both how far away those galaxies were and how fast they were receding, building a map of the universe's expansion history. Exploding stars became our rulers for measuring the cosmos. These supernovae appeared dimmer than expected, revealing the accelerating expansion. When the team studying distant Type Ia supernovae in the 1990s analyzed their data, they made a startling discovery. The supernovae appeared dimmer than they should have been, given the speed at which their host galaxies were receding from us, as though they were further away than expected. In a universe where expansion was slowing down, distant supernovae should have appeared brighter, not dimmer, because the galaxies would have been closer when the light was emitted. The only explanation for the unexpectedly dim supernovae was that the universe's expansion had actually been speeding up over cosmic history, pushing the galaxies farther away than a decelerating universe would have allowed. Dimmer light revealed a darker truth. The cosmos was accelerating into the void, and no one had seen it coming. The discovery of dark energy earned the 2011 Nobel Prize in Physics. The discovery that the expansion of the universe is accelerating was recognized in 2011 with the Nobel Prize in Physics, awarded to 3 astronomers whose teams had independently found the evidence for dark energy through their observations of distant supernovae, confirming the result through 2 separate research programs that reached the same astonishing conclusion using different data and different analysis methods. This recognition reflected not only the importance of the discovery, which fundamentally changed our understanding of cosmology, but also the rigorous scientific work that went into establishing the result beyond reasonable doubt, a process that took years of careful observation and analysis before the scientific community accepted that the acceleration was real. The prize celebrated a discovery that humbled humanity's picture of the universe. We learned we knew less than we thought. Saul Perlmutter, Brian Schmidt, and Adam Rees led the teams that discovered dark energy. The Nobel Prize for the discovery of dark energy was shared by Saul Perlmutter from the Supernova Cosmology Project and Brian Schmidt and Adam Rees from the HISE Supernova Search Team, 2 competing research groups that had been racing to measure the deceleration of the universe's expansion, but instead found, to their mutual astonishment, that the expansion was accelerating. Both teams were initially skeptical of their own results, checking and rechecking their data for errors, unable to believe that the cosmos could be behaving so unexpectedly, but as the evidence accumulated, they were forced to accept what the supernovae were telling them. The competition between the teams ultimately strengthened the discovery, as each served as a check on the other's work. Scientific rivalry led to cosmic revelation. Dark energy behaves like a property of space itself. Unlike ordinary matter or even dark matter, which exists within space and moves through it, dark energy appears to be a property of space itself, an intrinsic characteristic of emptiness that causes space to expand and stretch in all directions, not because something is pushing it from outside, but because expansion is simply what empty space does when dark energy is present. As the universe expands and more space comes into existence between the galaxies, more dark energy appears along with it, maintaining a constant density throughout the cosmos, no matter how large the universe becomes, a feature that distinguishes dark energy from all other known forms of matter and energy. This is why the effect of dark energy grows stronger over cosmic time. Space makes more of itself, and dark energy comes along for the ride. And as these vast ideas settle around you, there is no need to grasp them tightly. Let them drift past like stars outside a window. Breathe slowly and allow your thoughts to soften. The universe can hold its mysteries without your effort tonight. Einstein proposed a cosmological constant that behaves like dark energy. Nearly a century before the discovery of dark energy, Albert Einstein introduced a term into his equations of general relativity called the cosmological constant, a mathematical quantity that represented a kind of energy inherent in empty space, included not because Einstein believed it existed, but because he wanted his equations to describe a static universe that neither expanded nor contracted. At the time, most scientists believed the universe was eternal and unchanging, and Einstein added the cosmological constant to counteract the natural tendency of gravity to make everything collapse. When Edwin Hubble later discovered that the universe is actually expanding, Einstein reportedly called the cosmological constant his greatest blunder, removing it from his equations in embarrassment. But decades later, dark energy would bring it back. Einstein's mistake turned out to be prophetic. Einstein originally introduced the cosmological constant to create a static universe. In the early 20th century, When Einstein developed his theory of general relativity, the prevailing belief among scientists and philosophers was that the universe had always existed and would always exist, unchanging and eternal, a view that stretched back to ancient times and seemed self-evident to most thinkers of the era. But Einstein's equations naturally predicted that the universe should either be expanding or contracting under the influence of gravity, a result he found philosophically troubling, and so he introduced the cosmological constant as a kind of repulsive force that would exactly balance gravity, holding the universe in a delicate equilibrium. This modification was mathematically elegant but physically contrived, added not because there was evidence for it, but because Einstein wanted his equations to match his preconceptions about reality. Sometimes the greatest minds are also prisoners of their time. He later called this his greatest blunder, but it may have been prophetic. When Edwin Hubble discovered in 1929 that distant galaxies are receding from us, proving that the universe is expanding and not static as everyone had assumed, Einstein realized that his cosmological constant had been unnecessary, a mathematical patch applied to fix a problem that did not exist. And according to various accounts, he called this addition his greatest blunder or biggest mistake. Regretting that he had not trusted his original equations to reveal the truth about the cosmos. But history would vindicate Einstein's instinct if not his reasoning, because the discovery of dark energy nearly 70 years later showed that something very much like the cosmological constant does exist, a property of empty space that accelerates the expansion of the universe, just as his abandoned term would have predicted. Einstein's blunder became his legacy. Sometimes being wrong for the right reasons is still being right. The cosmological constant represents energy in empty space. In modern physics, the cosmological constant is understood as a measure of the energy density of empty space, the amount of energy contained in every cubic meter of vacuum, regardless of whether that space contains matter or radiation or anything else at all. A background energy that permeates the entire universe equally and drives the accelerating expansion we now observe. If the cosmological constant is positive, as observations suggest, then empty space itself has a positive energy density that acts as a kind of repulsive gravity, pushing space apart rather than pulling it together. And this energy does not dilute as the universe expands because new vacuum with the same energy density is constantly being created. This simple mathematical term captures one of the strangest properties of reality. Emptiness is not empty. Even nothing has energy. Vacuum energy in quantum physics may be related to dark energy. Quantum physics tells us that even completely empty space is not truly empty, but instead seethes with activity at the smallest scales, with virtual particles constantly flickering in and out of existence, borrowing energy from the vacuum for brief instants before annihilating and returning what they borrowed, a restless churning that gives empty space a measurable energy. Some physicists have proposed that this vacuum energy might be the source of dark energy, providing a natural explanation for why empty space would have intrinsic energy that causes it to expand. However, when physicists calculate the expected amount of vacuum energy using quantum field theory, they get a number that is absurdly larger than the observed dark energy, off by a factor of 10 to the power of 120, perhaps the worst prediction in the history of physics. The vacuum refuses to explain itself. And as we contemplate the energy of empty space, we now turn to the nature of dark energy and its strange, uniform presence throughout the cosmos. Dark energy has roughly the same density everywhere in the universe. One of the defining characteristics of dark energy is that it has the same density everywhere in the universe. Unlike matter, which clumps into galaxies and clusters, leaving vast empty regions in between, or radiation which spreads out and dilutes as the universe expands, dark energy maintains a constant energy per unit volume regardless of location or cosmic epoch, pervading the space between the galaxies just as thoroughly as the space inside your room. This uniformity is what makes dark energy so different from anything else we know, and it is also what allows its effects to grow over cosmic time, because as the universe expands and matter dilutes, the unchanging density of dark energy becomes relatively more important, eventually dominating the energy budget of the cosmos entirely. Dark energy does not concentrate or thin out. It simply is, everywhere and always, at the same density forever. Unlike matter, dark energy does not clump or concentrate. Matter, whether ordinary atoms or invisible dark matter, responds to gravity by falling inward toward regions of higher density, gathering into clumps and clusters and filaments that eventually become the galaxies and cosmic web we observe across the heavens. But dark energy shows no such tendency, remaining perfectly uniform throughout space, regardless of whether that space is filled with dense galaxy clusters or stretches through the emptiest cosmic voids. This refusal to clump is related to the negative pressure of dark energy, a property that causes it to push space apart rather than pull things together. And it is this spreading rather than gathering that makes dark energy fundamentally different from any other ingredient in the cosmos. Dark energy does not flow or collect. It simply fills space evenly. Uniformity is its defining characteristic. As the universe expands, more dark energy appears to fill the new space. As the universe expands and the distance between galaxies grows ever larger, the total amount of dark energy in the cosmos actually increases, because each new unit of space that comes into existence contains the same density of dark energy as every other unit of space, meaning that expansion does not dilute dark energy, but rather creates more of it, an ever-growing reservoir of energy that appears from nowhere and drives further expansion in a kind of cosmic feedback loop. This behavior is profoundly strange, as every other form of energy we know dilutes when the container expands, whether radiation spreading through growing space or gas molecules filling a larger chamber, but dark energy violates this intuition completely, maintaining its density while the volume increases and thereby growing without limit. The more space there is, the more dark energy there is. Expansion feeds upon itself. Dark energy exerts a negative pressure that pushes space apart. The physical mechanism by which dark energy causes the universe to accelerate involves a property called negative pressure, a concept that sounds paradoxical but emerges naturally from the equations of general relativity when energy has certain characteristics, causing space to expand rather than contract even in the presence of matter that would normally pull everything together. Normal pressure, like the air in a tire, pushes outward against the walls of its container, but negative pressure acts in the opposite sense, creating a kind of cosmic tension that stretches space itself, making the fabric of the universe pull apart rather than compress. This negative pressure is why dark energy dominates the expansion of the universe on the largest scales, overwhelming the attractive gravity of matter with a repulsive stretching of space that grows stronger as the cosmos expands. The universe is being pulled apart from within. This repulsive effect only becomes significant on the largest cosmic scales. Although dark energy permeates all of space equally, its repulsive effect on cosmic expansion only becomes significant on the very largest scales, across distances of millions or billions of light years, where the feeble push of dark energy can accumulate enough to overcome the attractive gravity of matter and accelerate the expansion of the universe. Within a galaxy like our Milky Way, The gravitational attraction between stars and dark matter is far stronger than the repulsive effect of dark energy, and so galaxies remain bound together despite the dark energy within them, orbiting their centers and maintaining their shapes across billions of years. Even clusters of galaxies, containing thousands of member galaxies bound by gravity, are immune to dark energy's push. Only on the grandest scales, where matter is sparse and distances are vast, does dark energy reign. The struggle between attraction and repulsion has been decided by scale. On the scale of galaxies and smaller, gravity still dominates. Despite the overwhelming abundance of dark energy in the cosmos, its effects are completely negligible on the scales of everyday life, on the scale of planets and stars, and even entire galaxies, where the attractive force of gravity pulling matter together is vastly stronger than the repulsive effect of dark energy pushing space apart. The Milky Way will not fly apart because of dark energy, nor will the solar system expand or the Earth drift away from the Sun, as the gravitational forces binding these systems together are trillions of times stronger than any stretching effect dark energy might produce at such small distances. You need not worry about dark energy affecting your body or your home or anything you can see with your eyes. Dark energy is patient, working only across unimaginable distances. It leaves the small things alone. Dark energy affects the universe only where distances are measured in millions of light years. The influence of dark energy becomes measurable only across the vastest distances, where the expansion of space between distant galaxy clusters proceeds fast enough to be accelerated by the repulsive effect of dark energy, stretching the fabric of the cosmos faster and faster as the eons pass. At these scales, millions or billions of light years, the cumulative effect of dark energy overwhelms the weakened gravity between widely separated structures, and the universe begins to pull apart more quickly than gravity can hold it together. Astronomers observe this acceleration by measuring the redshifts of distant galaxies and supernovae, tracking the rate at which the universe expands across cosmic history, and finding that the expansion has been speeding up for the last 5 billion years. Dark energy whispers only to the largest things. Its voice carries across the emptiness between galaxy clusters. The ratio of dark energy to matter changes as the universe expands. In the early universe, when everything was packed more closely together and space was much smaller than it is today, the density of matter was far higher than the density of dark energy, and gravity dominated the evolution of the cosmos, pulling matter into the first clumps and structures that would eventually become galaxies. But as the universe expanded and matter spread out and diluted, the constant density of dark energy became relatively more important, because dark energy does not dilute when space expands, remaining at the same density while matter becomes ever more sparse. Eventually, a few billion years ago, dark energy crossed a threshold where it began to dominate the total energy budget of the universe, and its repulsive effect started accelerating the expansion. The balance has shifted. Darkness now outweighs everything else. Dark energy became dominant over matter about 5 billion years ago. For most of cosmic history, the universe was dominated first by radiation and then by matter, with gravity controlling the expansion rate and gradually slowing it down as matter pulled against the outward momentum of the Big Bang. But about 5 billion years ago, roughly when the Sun and Earth were forming, dark energy finally accumulated enough relative importance to begin accelerating the expansion, marking a turning point in cosmic evolution after which the universe entered an era of ever faster growth. Before this transition, galaxies were still being drawn toward each other on the largest scales, forming the clusters and superclusters we observe today. But after dark energy took over, this process of structure formation began to slow, and distant regions of the cosmos started receding more quickly. The transition happened quietly, unmarked by any cosmic event. We were born in the era of acceleration. Before that, dark matter and gravity controlled the evolution of the universe. During the first 9 billion years of cosmic history, the evolution of the universe was dominated by the gravitational effects of matter, mostly dark matter, which controlled how fast the cosmos expanded and how structures formed within it, pulling gas and dust into the gravitational wells that would eventually host galaxies and clusters. Dark energy existed during this era, but was not yet strong enough relative to matter to influence the expansion rate, sitting quietly in the background while gravity shaped the cosmic landscape, building the filaments and nodes of the cosmic web from the primordial fluctuations seeded after the Big Bang. Only as the universe expanded and matter diluted did dark energy step forward, inheriting a cosmos already sculpted by gravitation, but destined to be transformed by acceleration. The age of building ended. The age of dispersal began. And as we trace the shifting balance between darkness and light, we now consider the future that dark energy may bring. In the distant future, dark energy will push galaxies beyond our view. If dark energy continues to accelerate the expansion of the universe at its current rate, which most cosmologists expect it will, then the distant future holds a cosmos very different from the one we see today, as galaxies beyond our local group will be pushed outward faster and faster until they recede from us at speeds exceeding the speed of light, their light stretched to infinity and their images fading from the observable universe forever. This will not happen suddenly, but gradually over billions and trillions of years, as the accelerating expansion carries distant structures ever further away, beyond the cosmic horizon from which light can ever reach us. The night sky will eventually darken, not because the stars have all died, but because the galaxies have been carried beyond the edge of visibility. The cosmos is slowly erasing itself from view. Eventually, only our local group of galaxies will remain visible. Trillions of years from now, if dark energy continues its work, the accelerating expansion of space will have pushed every galaxy beyond our local group. The small cluster containing the Milky Way, Andromeda, and a few dozen smaller companions, beyond the cosmic horizon from which light can ever reach us, leaving future astronomers with a sky containing only nearby stars and no evidence that the vast universe of billions of galaxies ever existed at all. The Milky Way and Andromeda will have merged by then into a single giant elliptical galaxy, drifting alone through an apparently empty cosmos, surrounded by an ever-growing horizon of darkness beyond which nothing can be seen or detected. The universe will seem much smaller than it actually is. Future civilizations may never know what they have lost. Distant galaxies will appear to accelerate away faster than the speed of light. As the expansion of the universe accelerates, distant galaxies will eventually recede from us at speeds exceeding the speed of light, a statement that sounds impossible but does not violate any law of physics, because it is not the galaxies themselves that are moving faster than light, but rather the space between us and them that is expanding at this rate, stretching faster than light can travel across it. Nothing can move through space faster than light, but space itself can expand at any rate whatsoever, and in a universe dominated by dark energy, the expansion rate at great distances inevitably exceeds the cosmic speed limit. Light from these receding galaxies will be stretched to ever longer wavelengths, redshifted first into infrared, and then into radio waves, and finally into wavelengths too long to detect. They will not explode or vanish. They will simply fade beyond all possible observation. This is possible because space itself is expanding, not the galaxies moving through it. The expansion of the universe is fundamentally different from ordinary motion. Not a case of galaxies flying through space like shrapnel from an explosion, but rather a stretching of space itself, with galaxies carried along passively as the fabric of the cosmos expands beneath them. And this distinction is crucial for understanding how galaxies can recede faster than light without violating the cosmic speed limit. When space expands, it does not move objects through space, but rather increases the distance between objects by creating more space in between them, a process that has no speed limit because no object is actually traveling at any particular velocity relative to its local surroundings. The galaxies are not moving. The space between them is growing. This is why the light speed barrier does not apply. Light from these distant galaxies will be stretched into invisibility. As distant galaxies recede from us at ever-increasing speeds due to the accelerating expansion of space, the light they emit gets stretched to longer and longer wavelengths through a process called cosmological redshift, shifted from visible light into infrared, and then into microwaves and radio waves, and eventually into wavelengths so long that no conceivable detector could ever register them, essentially fading to black even though the galaxies continue to shine as brightly as ever in their own reference frames. This stretching happens continuously as the light travels across expanding space, accumulating over billions of years until the original photons bear no resemblance to their initial state, their energy diluted to nearly nothing by the relentless growth of the cosmos. The galaxies are not going dark. Their light is simply being stretched beyond all detection. Expansion eventually silences everything. Future astronomers may see only a lonely universe of nearby stars. If intelligent life still exists trillions of years from now, and if those beings look out at their night sky, they will see something very different from what we see today, not the rich tapestry of billions of galaxies, but only the merged remnant of the Milky Way and Andromeda, a single giant galaxy surrounded by darkness in every direction, with no evidence that the vast universe we now observe ever existed. The accelerating expansion will have carried all other galaxies beyond the cosmic horizon, their light stretched to undetectable wavelengths, and the cosmic microwave background will have faded to nothing, leaving no trace of the Big Bang or the universe's large-scale structure. These future astronomers may conclude their galaxy is all that exists. They will be wrong, but they will have no way to know it. They might never know that billions of galaxies once filled the sky. The tragedy of the distant future, if tragedy is the right word for events so far removed from human experience, is that evidence of the true nature of the universe will have been erased by the very expansion that reveals it to us today, leaving future observers with no way to reconstruct the cosmic history we now understand so well. The galaxies will have vanished beyond all horizons, the cosmic microwave background will have redshifted to undetectability, and even the chemical elements forged in the Big Bang will have been recycled through so many generations of stars that their primordial origins will be obscured beyond recovery. All the evidence that led us to discover dark matter and dark energy will have faded into oblivion. We live in a special time when the universe reveals its secrets. Future ages will inherit only silence. The cosmic microwave background will eventually redshift beyond detection. The cosmic microwave background, that faint glow of radiation left over from the early universe that has taught us so much about the Big Bang and the nature of dark matter and dark energy, will eventually be stretched by cosmic expansion to wavelengths so long that no instrument could ever detect it, fading from the universe like a voice growing too faint to hear, carrying with it all the information it once contained about the first moments of creation. This radiation has already been stretched from the hot visible light it once was to the cool microwave frequencies we detect today, And as the universe continues to expand, it will stretch further still into radio waves and beyond, until the photons that have traveled for nearly 14 billion years finally become unobservable. The oldest light in the universe will eventually disappear. The echo of creation will fall silent. Evidence of the Big Bang itself will fade from any observable record. The most profound consequence of the accelerating expansion may be that all evidence for the Big Bang, for the hot, dense state from which the universe emerged nearly 14 billion years ago, will eventually become unobservable, leaving future scientists with a cosmos that appears static, eternal, and alone, with no way to know that it began in fire and has been expanding ever since. The cosmic microwave background will have faded, the light from distant galaxies will have stretched beyond detection, and even the relative abundances of hydrogen and helium forged in the first few minutes will have been processed through countless stars until their primordial proportions can no longer be measured. The very idea that the universe had a beginning will become unprovable. Knowledge itself will be erased by expansion. We live in a special era when the full history of the universe is still visible. Right now, in this brief window of cosmic time, we have access to an extraordinary wealth of information about the universe's past and present, from the cosmic microwave background that tells us about conditions just after the Big Bang, to the light from billions of galaxies that reveals the large-scale structure of the cosmos, to the supernovae that allowed us to discover dark energy accelerating the expansion. Future observers, gazing out from a lonely galaxy island after all the evidence has faded, will have none of these tools, no way to reconstruct the story we now read so clearly in the sky. We are privileged witnesses to a cosmos that still reveals its history, a universe that has not yet hidden itself from view. This is a special time. The darkness has not yet won. And in this moment, resting quietly in this special era, you are part of the universe witnessing itself. Let that thought settle gently like dust in starlight. There is nothing more you need to hold. Just breathe and let the cosmos breathe with you. The ultimate fate of the universe depends on the nature of dark energy. How the universe will end, if indeed it ends at all, depends critically on what dark energy actually is and whether its properties remain constant over cosmic time or change as the universe evolves, a question that remains unanswered despite decades of observation and theoretical effort. If dark energy is truly a cosmological constant with the same density everywhere and everyone, then the universe will expand forever, gradually cooling and dimming as stars burn out and matter spreads thin, approaching a cold, dark emptiness, sometimes called heat death. But if dark energy is something more dynamic, something that can strengthen or weaken over billions of years, then the future might hold very different fates, from a big rip that tears everything apart to a collapse back to a fiery singularity. The ending has not yet been written. We know only that darkness will decide it. If dark energy remains constant, the universe will expand forever. The most likely scenario for the future of the cosmos, based on current observations suggesting that dark energy behaves like a true cosmological constant with unchanging density, is that the universe will continue expanding and accelerating forever, with the distances between galaxy clusters growing without limit, and the cosmos gradually cooling and dimming as the stars within each isolated island burn through their fuel and fade to darkness. Trillions of years from now, the last stars will flicker out, leaving behind a universe of dead stellar remnants, black holes, and slowly cooling matter, drifting through an emptiness so vast and so permanent that nothing will ever change again. All energy spread so thinly that no work can be done and no life can exist. This is called heat death, the ultimate triumph of entropy. The universe will not end with a bang, but with an eternal whisper. If dark energy strengthens, a big rip could tear apart all matter. One possible future for the universe, permitted by certain theoretical models of dark energy, is a scenario called the Big Rip, in which dark energy grows stronger over time, its repulsive effect increasing until it overwhelms not just the gravity binding galaxy clusters together, but the forces holding galaxies themselves together. Then stars, then planets, then molecules, then atoms. Tearing the fabric of reality apart completely in a final catastrophic moment, some tens of billions of years from now. In this scenario, the accelerating expansion would eventually overcome every attractive force in nature, ripping apart the structures that have taken billions of years to form, until not even subatomic particles could hold together, and space itself might cease to have any coherent structure at all. This outcome is not considered likely, but it cannot be ruled out with current data. The universe might die by being torn asunder. In a Big Rip scenario, galaxies, stars, planets, and atoms would be torn apart. Should the Big Rip actually occur, the destruction would proceed in stages, with the largest structures succumbing first and ever smaller objects following as dark energy's repulsive effect grows stronger, first tearing apart the bonds between galaxy clusters, then between individual galaxies within clusters, then between stars within galaxies, then between planets and their host stars, until finally, in the last fractions of a second, the forces holding molecules together would be overwhelmed, then atoms themselves would be torn apart, and perhaps even the protons and neutrons at the heart of matter would be ripped into their constituent quarks. The entire history of the universe, all the structure painstakingly built up over billions of years by gravity working against the expansion, would be undone in a final catastrophic unwinding. Everything constructed would be destroyed. The cosmos would return to chaos. If dark energy weakens, the universe might eventually collapse. Although current observations suggest that dark energy is either constant or strengthening, some theoretical models allow for the possibility that dark energy could weaken over cosmic time, eventually fading to zero, or even becoming attractive rather than repulsive, which would allow gravity to reassert its dominance and begin pulling the universe back together in a reversal of the expansion that has defined cosmic history since the Big Bang. Should this occur, the universe would eventually stop expanding and begin to contract, slowly at first, and then faster and faster, with galaxies approaching one another, temperatures rising, and space collapsing back toward the dense hot state from which everything emerged, possibly ending in a big crunch that mirrors the Big Bang in reverse. Some speculate that such a collapse could lead to a new Big Bang. The universe might be cyclic, dying and being reborn forever. And from these possible endings, we now turn back to the present, where scientists work to understand what dark matter and dark energy truly are. Direct detection experiments search for dark matter particles underground. Deep beneath mountains and abandoned mines around the world, scientists have built detectors of extraordinary sensitivity, shielded from the cosmic ray bombardment that strikes the surface, waiting for the rare moment when a dark matter particle might collide with an ordinary atom and leave a trace. These experiments are placed underground because even a single cosmic ray interaction would overwhelm the faint signal that dark matter might produce. So laboratories have been built under kilometers of rock, where the overburden filters nearly all background radiation. The detectors use various technologies, from noble liquids that flash with light when struck to crystals that warm upon impact, each designed to catch different dark matter signatures. So far, no confirmed detection has been made. The darkness remains silent, but the vigil continues. These detectors use ultra-pure materials to reduce background noise. The materials used in dark matter detectors must be purified to levels achieved nowhere else in human technology, because even trace amounts of naturally occurring radioactive isotopes would create signals that overwhelm any possible dark matter interaction, producing a constant background of events that would make detecting the genuine signal like trying to hear a whisper during a thunderstorm. Scientists go to extraordinary lengths to achieve this purity, selecting materials from ancient sources with low radioactivity, processing them in clean rooms to remove contaminants, and shielding them with layers of lead, copper, and water to block external radiation. Some experiments use xenon that has been purified through repeated distillation until fewer than 1 atom in a billion is anything other than xenon. Others use crystals grown in controlled conditions over years. The search for the invisible requires materials of impossible cleanliness. Even the faintest cosmic ray must be shielded in dark matter experiments. Cosmic rays, those high-energy particles raining down constantly from space, striking the atmosphere and producing cascades of secondary particles, are the enemy of dark matter detection, producing signals indistinguishable from the interactions scientists hope to observe. To escape this bombardment, experiments are placed deep underground where rock absorbs most cosmic rays before reaching the detector. But even this is not enough, because radioactive decay in the rock and detector materials produces its own background that must be distinguished from potential dark matter signals. Every component is selected for low radioactivity, every surface cleaned obsessively, and sophisticated techniques employed to reject non-dark matter events. The detectors float in pools of purified water. Silence must be absolute for the invisible to speak. Xenon detectors are among the most sensitive dark matter instruments. Among the most successful technologies for dark matter detection are detectors using liquid xenon, a noble gas cooled to temperatures far below freezing, which has the useful property that when a particle interacts with it, the collision produces both a flash of light and a small number of electrons that drift upward through the liquid and can be detected separately, allowing scientists to measure both signals and use the ratio between them to distinguish between different types of particles. This dual detection capability helps reject the many background events that would otherwise mimic dark matter signals, making xenon detectors extraordinarily sensitive to the faint interactions that dark matter might produce. The largest xenon experiments now contain multiple tons of the ultrapure liquid, surrounded by arrays of sensitive light detectors that can register even a single photon. In this chamber of liquid light, scientists listen for the darkness. The LuxZePLIN experiment uses 10 tons of liquid xenon to search for WIMPs. Deep underground in South Dakota, in a cavern excavated from the rock of a former gold mine, the LuxZePLIN experiment, or LZ for short, holds 10 tons of ultrapure liquid xenon in a titanium vessel surrounded by layers of shielding, waiting for the rare collision that might reveal the nature of dark matter after decades of searching. This experiment represents the culmination of years of development in xenon detector technology, combining the expertise of multiple research groups to build the most sensitive dark matter detector yet constructed, capable of detecting interactions so rare that they might occur only a few times per year, despite the tons of material watching. The xenon is continuously purified to remove any contaminants. The detector is monitored around the clock, and elaborate calibration procedures ensure that any genuine signal can be distinguished from background. The mine that once sought gold now seeks something far more valuable. Space-based telescopes map dark matter through gravitational lensing, while underground experiments search for individual dark matter particles. Telescopes in space take a different approach. mapping the distribution of dark matter across cosmic scales by measuring how its gravity bends and distorts the light from distant galaxies, creating subtle patterns of distortion that reveal the presence and arrangement of matter that cannot be seen directly. This technique, called gravitational lensing, turns the entire universe into a natural laboratory for studying dark matter, using the light from billions of galaxies as probes that pass through the dark matter structures between those galaxies and us, arriving slightly distorted in ways that careful measurement can detect. Space-based observations are particularly valuable because the Earth's atmosphere blurs images and makes the precise shape measurements needed for lensing analysis more difficult. From above the atmosphere, telescopes can measure galaxy shapes with exquisite precision. The distortions reveal the invisible. The Euclid space mission launched in 2023 to study dark energy and dark matter. In July of 2023, the European Space Agency launched the Euclid Space Telescope, a sophisticated observatory designed specifically to study dark energy and dark matter by surveying billions of galaxies across more than a third of the entire sky, using two complementary instruments to measure both the visible light and near-infrared emissions from galaxies up to 10 billion light-years away. From its position at the second Lagrange point, 1.5 million kilometers from Earth, Euclid will create the most detailed three-dimensional map of the universe ever made, tracking how the distribution of matter has changed over cosmic history and measuring the subtle distortions in galaxy shapes caused by gravitational lensing with unprecedented precision. The mission represents Europe's most ambitious contribution to dark sector research. Named after the ancient Greek mathematician, Euclid will chart the geometry of the cosmos. Euclid will observe billions of galaxies over 6 years. Over the course of its 6-year mission, the Euclid Space Telescope will systematically photograph and catalog billions of galaxies, measuring their positions, distances, and shapes with precision sufficient to detect the subtle gravitational effects of dark matter, and to track how the distribution of matter has evolved under the influence of dark energy over cosmic time. This vast dataset will allow scientists to test whether dark energy behaves like a true cosmological constant with the same strength everywhere and everyone, or whether it is something more dynamic that changes over the history of the universe, a distinction that could reveal fundamental truths about the nature of space, time, and energy. Each galaxy measured is itself a cosmos of hundreds of billions of stars, yet to Euclid they are merely points of light whose positions and shapes carry information about the darkness that shapes them. Billions of worlds serve as probes of the invisible. The Vera C. Rubin Observatory will map dark matter across the southern sky. The Vera C. Rubin Observatory, currently being completed in Chile, will conduct the most comprehensive survey of the night sky ever attempted, photographing the entire visible southern sky every few nights for a decade, and creating a moving picture of the universe, revealing billions of galaxies and unprecedented data for studying dark matter and dark energy. Named after the astronomer whose observations provided early evidence for dark matter in galaxies during the 1970s, the observatory's camera, the largest ever built for astronomy, will capture images so detailed that subtle distortions from dark matter's gravitational effects can be measured across billions of galaxies. By tracking these patterns over cosmic time, Rubin will test whether dark energy is constant or evolving. The observatory honors a pioneer who helped reveal the darkness. These surveys create three-dimensional maps of dark matter distribution. By combining measurements of galaxy positions with estimates of their distances, determined from how much their light has been stretched by cosmic expansion, and with measurements of the subtle distortions in their shapes caused by gravitational lensing, astronomers can construct three-dimensional maps showing how dark matter is distributed throughout the universe, revealing the cosmic web of filaments and voids that gravity has sculpted over billions of years. These maps show dark matter concentrated in sheets and filaments that stretch across hundreds of millions of light years, surrounding vast empty voids where little matter of any kind exists, with galaxies scattered along the densest regions like beads on cosmic strings. The structure revealed by these maps matches remarkably well with computer simulations of how dark matter should cluster under gravity's influence, providing powerful evidence that the dark matter model correctly describes reality. We have mapped the invisible. The darkness has a geography. And from the instruments that search for darkness, we now consider the theories that try to explain it. Modified gravity theories suggest dark matter might not exist at all. The continued failure to directly detect dark matter particles has led some physicists to reconsider whether dark matter exists at all, proposing instead that the gravitational anomalies attributed to dark matter might result from our incomplete understanding of gravity itself, that perhaps Einstein's general theory of relativity, so successful in other contexts, needs to be modified when applied to the extremely weak gravitational fields found in galaxies and galaxy clusters. These modified gravity theories attempt to explain the same observations that dark matter explains: the flat rotation curves of galaxies, the motions of galaxies within clusters, the patterns in the cosmic microwave background, without invoking any new form of matter, instead changing the rules of gravity to produce the same effects. Such theories remain controversial, and most physicists still favor the dark matter explanation. But the failure to find particles has kept the alternatives alive. MOND proposes that gravity behaves differently at very low accelerations. The most famous modified gravity theory is called MOND, an acronym for Modified Newtonian Dynamics, proposed in 1983 by physicist Mordechai Milgram, which suggests that Newton's second law of motion, the fundamental relationship between force, mass, and acceleration, breaks down at the extremely low accelerations found in the outer regions of galaxies, where the gravitational pull is so weak that particles experience accelerations billions of times smaller than we feel on Earth. In MOND, gravity becomes effectively stronger at these low accelerations, holding the outer particles of galaxies in faster orbits than standard physics would predict, exactly matching the flat rotation curves that led to the dark matter hypothesis without requiring any invisible matter. The theory successfully predicts the rotation curves of many galaxies with remarkable precision, yet explaining all the evidence attributed to dark matter has proved more challenging. However, MOND struggles to explain observations like the bullet cluster. The greatest challenge facing modified gravity theories like MOND is explaining observations where dark matter and ordinary matter appear to be separated from each other, as seen most dramatically in the bullet cluster, where two galaxy clusters have collided, and the hot gas that makes up most of the ordinary matter has been slowed by the impact, while the gravitational lensing signal, which reveals where the mass is concentrated, has continued moving with the galaxies themselves. In a universe without dark matter, the gravitational lensing signal should follow the hot gas, where most of the ordinary mass resides, but instead it tracks something invisible that has passed through the collision unimpeded, exactly as dark matter would behave. Modified gravity theories struggle to explain how gravity can be strongest where the matter is not. This observation is often cited as proof that dark matter genuinely exists. Most physicists believe dark matter particles are more likely than modified gravity. Despite the failure to directly detect dark matter particles after decades of searching, and despite the limited success of modified gravity theories in explaining some observations, the overwhelming consensus among physicists remains that dark matter is real, that it consists of some form of particle or particles not yet discovered, and that the gravitational anomalies observed throughout the universe genuinely reflect the presence of vast amounts of invisible matter rather than a breakdown of our understanding of gravity. This consensus rests on the remarkable success of the dark matter model in explaining such a wide range of observations, from the rotation of individual galaxies to the structure of the cosmic web to the precise patterns in the cosmic microwave background, a success that no modified gravity theory has yet matched. The particles may be harder to find than expected, but the evidence for their existence remains compelling. Primordial black holes have been proposed as a dark matter candidate. One alternative to particle dark matter that has attracted renewed interest is the possibility that dark matter consists not of new particles, but of black holes formed in the first moments after the Big Bang, when extreme density fluctuations might have caused some regions to collapse directly into black holes without forming stars, creating a population of primordial black holes that could still exist today. These black holes would behave gravitationally exactly as dark matter does, holding galaxies together and creating the cosmic web without emitting light, and being made of ordinary matter collapsed into extreme density, they would not appear in detection experiments designed for new particles. The idea is elegant and avoids new physics, but observations have placed strict limits on how much dark matter could consist of primordial black holes. These would be black holes formed in the first second after the Big Bang. Unlike the black holes that form today from collapsing massive stars, primordial black holes would have formed in the first second after the Big Bang, when the universe was so dense that small density fluctuations could create regions where gravity overwhelmed the pressure pushing outward, causing matter to collapse into black holes without passing through the stellar phase. These primordial black holes could range in mass from less than an atom to thousands of times the Sun's mass, depending on when they formed, and the lightest would have evaporated by now through Hawking radiation, while heavier ones would still exist, roaming as invisible gravitational influences. If they exist in sufficient numbers, they could account for some or all of dark matter, ancient darkness born in the first moment of creation. Observations have ruled out many primordial black hole mass ranges. The primordial black hole hypothesis, while elegant, faces significant observational constraints, as astronomers have searched for evidence of such black holes across a wide range of possible masses and ruled out many scenarios that would have produced detectable effects, from the gravitational lensing that large numbers of black holes would produce as they pass in front of distant stars, to the disruption of binary star systems by wandering black holes, to the gravitational waves that merging primordial black holes would generate. These searches have excluded primordial black holes as the sole explanation for dark matter across most of the mass range where they might plausibly exist, though narrow windows remain where they could still contribute significantly, particularly in mass ranges where detection is most difficult and constraints are least restrictive. The idea has not been killed, but it has been severely wounded. Only narrow refuges remain for this ancient darkness. Sterile neutrinos are another particle that could make up dark matter. Among particle candidates for dark matter, sterile neutrinos hold a special place as a possibility emerging naturally from attempts to explain other puzzles in particle physics, particularly the fact that ordinary neutrinos have mass when the simplest standard model predicted they should be massless. Sterile neutrinos would be heavier relatives of ordinary neutrinos, interacting with matter only through gravity and perhaps through extremely rare mixing processes with their lighter cousins, making them virtually undetectable while still allowing them to have been produced in quantities sufficient for dark matter. They would be warm dark matter rather than cold, moving at significant speeds in the early universe and smoothing out small-scale structure in ways that might explain some observations cold dark matter struggles with. The humble neutrino's heavier sibling might comprise the darkness. Dark photons are hypothetical particles that interact only with dark matter. Some theories propose that dark matter might have its own force carriers, analogous to the photons that carry the electromagnetic force between ordinary charged particles. These dark photons would mediate interactions among dark matter particles without coupling to ordinary matter at all, or coupling only through extremely faint mixing with ordinary photons that might produce subtle signals in sensitive experiments. If dark photons exist, dark matter would not be the simple, non-interacting substance often described, but would have its own rich physics, with dark matter particles pushing and pulling on each other through forces we cannot directly see, potentially forming structures and behaving in ways more complex than simple gravitational interaction would suggest. This opens the possibility of a hidden dark sector, an entire realm of physics occurring all around us but utterly invisible to our senses and instruments. Light we cannot see, illuminating matter we cannot touch. A hidden dark sector might contain its own particles and forces. The most exotic possibility for dark matter is that it is not a single particle, but the visible tip of a hidden dark sector, an entire parallel world of particles and forces that interacts with our world only through gravity, containing perhaps its own equivalents of electrons and protons, its own atoms and molecules, its own chemistry, and perhaps even its own complexity, all utterly invisible to us because the forces that bind it together are not the forces we can detect. Such a dark sector could contain structures we can scarcely imagine, organized by physics we know nothing about, coexisting with us in the same space, but separated by the unbridgeable gap between the forces that govern each world. This is speculation beyond what current evidence supports, a flight of imagination into the darkness. But physics allows it, and the darkness keeps its secrets. We know only what gravity reveals. And as these possibilities multiply like stars in the darkness, you do not need to choose among them. Let the theories rest, let the particles remain unseen. Your only task is to breathe, to feel the weight of your body, and to let yourself drift in the company of the unknown. Dark matter and dark energy are fundamentally different phenomena. Despite their similar names and the darkness that defines them both, dark matter and dark energy are fundamentally different phenomena that share almost nothing in common except our ignorance about their true nature. One being a form of matter that clusters under gravity and helps build the structures we see in the universe. The other being a property of space itself that drives the accelerating expansion and will eventually isolate every galaxy in its own cosmic horizon. Dark matter pulls things together, creating the galaxies and clusters and filaments that make up the cosmic web, while dark energy pushes things apart, fighting against gravity on the largest scales and winning, its influence growing stronger as the universe expands while dark matter's density thins. They are opposite forces shaped by common ignorance. The darkness has two faces that look nothing alike. Dark matter attracts through gravity, while dark energy pushes space apart. The essential difference between dark matter and dark energy lies in what each does to the universe, with dark matter behaving like ordinary matter in its gravitational effects, attracting other matter toward itself and helping to build the structures we see in the cosmos, while dark energy does the opposite, creating a repulsive effect that pushes space apart and accelerates the expansion of the universe on the largest scales. Dark matter is a form of stuff, something that exists in specific places and clumps together under its own gravity, while dark energy is more like a property of empty space itself, present everywhere in equal density and pushing outward uniformly in all directions. One builds structure, the other destroys it. One brought galaxies into being, the other will eventually scatter them beyond all horizons. They share only their invisibility and our ignorance of what they truly are. Despite their names, dark matter and dark energy may be completely unrelated. The similar naming of dark matter and dark energy, both containing the word dark, might suggest they are related phenomena, perhaps aspects of the same underlying mystery, but there is currently no evidence for any connection between them beyond the coincidence that both remain unexplained by known physics, and they could be as unrelated to each other as apples and automobiles, two mysteries that happen to coexist in the same universe without any deeper link. The dark in their names refers only to our inability to see them directly, to our ignorance about their true nature, not to any physical property they share, and solving the mystery of one would not necessarily tell us anything about the other. They might spring from the same exotic physics, or they might arise from completely different sources. The universe is under no obligation to make its mysteries conveniently connected. Some theories propose a unified dark fluid combining both. Despite the lack of evidence for any connection between dark matter and dark energy, some theorists have proposed unified models in which both phenomena arise from a single dark fluid that behaves differently on different scales, clustering like dark matter on galactic scales, where its self-attraction dominates, while pushing space apart on cosmic scales, where its repulsive pressure takes over, explaining both mysteries with a single exotic substance. These unified dark fluid models are mathematically elegant and scientifically appealing, reducing two mysteries to one, but they face significant challenges in matching all the observations that the separate dark matter and dark energy models explain, and most physicists consider them speculative proposals rather than well-established theories. The idea that the darkness might be unified is seductive, but nature is not required to satisfy our desire for simplicity. Quintessence is a model where dark energy changes over time. While the simplest model for dark energy treats it as a true cosmological constant with exactly the same density everywhere and everyone, an alternative model called quintessence proposes that dark energy is actually a dynamic field that can change over cosmic time, strengthening or weakening as the universe evolves, and potentially leading to futures very different from the eternal expansion that a constant dark energy would produce. In quintessence models, dark energy is a fifth fundamental essence permeating the cosmos, hence the name drawn from ancient Greek philosophy, a field that slowly evolves and whose changing properties could eventually reveal themselves in precision measurements of how the expansion of the universe has changed over cosmic history. Current observations are consistent with a true cosmological constant, but they cannot rule out quintessence models where the changes are small enough to have escaped detection so far. The darkness might be evolving even now. And as we consider these final mysteries, we turn to what the darkness tells us about our place in the cosmos. Ordinary matter makes up less than 5% of the universe. When we add together all the atoms that make up stars and planets, all the gas drifting between galaxies, all the dust and debris scattered through space, all the ordinary matter of every kind that exists anywhere in the observable universe, it adds up to less than 5% of the total energy content of the cosmos, a startlingly small fraction that means everything we can see, everything we can touch, everything science has studied directly for centuries. is a minor component of a universe dominated by darkness. Dark matter contributes about 27% and dark energy about 68%, together comprising 95% of the universe while remaining almost completely mysterious, their presence known only through their gravitational effects, while their true nature escapes our understanding. We are a minority in our own cosmos. The visible is a small island in an ocean of darkness. Everything we can see, touch, and measure is a tiny fraction of reality. The profound implication of living in a universe dominated by dark matter and dark energy is that everything human beings have ever experienced directly, every rock and tree and star, every atom studied in laboratories, every particle making up our bodies and the ground beneath our feet, represents a tiny, unrepresentative sample of what the cosmos actually contains. A small bright corner of a vast dark room whose full extent remains hidden from our senses and largely from our instruments. Science has revealed that the world we perceive is not the whole of reality, but merely the thin visible skin on a much larger universe, most of which exists in forms we cannot see and do not understand, interacting with our world only through gravity. We are tourists who have seen only the lobby. The greater mansion remains unexplored. The atoms in your body are among the rarest ingredients in the cosmos. The atoms that make up your body, the carbon in your cells, the oxygen you breathe, the calcium in your bones, belong to that rare minority called ordinary matter, less than 5% of the universe's contents, making you a concentration of cosmically unusual material, assembled into a pattern capable of wondering about the dark matter and dark energy that surround you in far greater abundance. Every atom in your body was forged in a star or in the explosive death of a star, created through nuclear reactions that transformed the primordial hydrogen and helium of the early universe into the heavier elements that make complex chemistry possible, and then scattered across space to eventually condense into planets and people. You are made of stellar ash, ordinary matter in an extraordinary arrangement. In a cosmos of darkness, you are a small point of rare, visible light. You are made of the visible minority in an invisible universe. To be human is to be made of ordinary matter, that rare substance comprising less than 5% of the universe, while all around you flows the dark matter and dark energy that make up the vast invisible majority, present at this moment in the room where you rest, passing through your body without interacting, shaping the universe you inhabit without touching you. You are a small collection of atoms organized into a pattern that can think, that can wonder, that can look out at a universe mostly made of things you cannot see and ask what they are, a brief flicker of awareness in a cosmos of darkness. You belong to the visible minority, the questioning few. You are ordinary matter, and that is extraordinary. Dark matter and dark energy surround us at this very moment. Right now, at this very moment, as you listen to these words, dark matter particles are streaming through the room where you rest, through your body, through the planet itself, trillions upon trillions of unseen particles passing without a trace, because they do not interact with the atoms of which you are made, except through the faint whisper of gravity, too small to notice on human scales, but sufficient to hold galaxies together across distances light takes thousands of years to cross. And through that same space, dark energy permeates every cubic centimeter, a constant presence that reveals itself only on the largest cosmic scales, but is as real here as it is in the voids between galaxy clusters billions of light years away. You are embedded in darkness, swimming in an invisible ocean that touches you without your knowledge. The mystery surrounds you as you drift towards sleep. The universe is mostly made of things we cannot see or understand. The most humbling lesson from dark matter and dark energy is how little we truly understand about the cosmos, a universe where the things we can see and study directly make up less than 5%. while 95% consists of substances whose nature remains unknown despite decades of research by brilliant scientists using sophisticated instruments. We have mapped dark matter across billions of light years, measured the acceleration of expansion with extraordinary precision, developed theories about what dark matter and dark energy might be, and yet we still do not know what either actually is, cannot point to a dark matter particle in a detector, cannot explain why empty space carries the energy that drives expansion. The darkness reminds us how much we have yet to learn. After decades of searching, dark matter and dark energy remain unexplained. After more than 9 decades since dark matter's first hints appeared in Fritz Zwicky's observations, and more than 2 decades since dark energy was discovered in supernova measurements, after thousands of papers and dozens of experiments and countless hours of thinking by brilliant physicists, dark matter and dark energy remain fundamentally unexplained, their existence established beyond doubt, but their true nature as mysterious as ever. Persistent puzzles that resist every attempt to crack them open. We know they exist, we know how much of each there is, we know how they behave on cosmic scales, and we know almost nothing else. Our understanding plateaued at a cliff beyond, which lies unexplored territory. The darkness keeps its secrets. We continue searching in patient hope. The darkness teaches us how much remains to be discovered. Perhaps the deepest meaning of dark matter and dark energy is not any specific fact about invisible particles or accelerating expansion, but the reminder they provide that the universe is far larger and stranger than we once imagined, that science is not nearly finished with its work of understanding, that mysteries as fundamental as what 95% of the cosmos is made of remain to be solved by future generations who may look back on our current ignorance the way we look back on those who thought the Earth was the center of everything. The darkness is not a failure of science, but an invitation to continue, a promise that discovery is not over, a sign that wonder and curiosity still have work to do in a universe that continues to surprise us with its depth and complexity. There is comfort in not knowing everything. The darkness leaves room for dreams. And with that, the story of dark matter and dark energy grows quiet. From the spinning galaxies held together by invisible hands to the empty space that pushes the cosmos apart. From the underground detectors waiting for a single collision to the telescopes mapping shadows across billions of light years. From the equations that hint at answers to the mysteries that still elude us. We have wandered through the darkness and found that the darkness is most of what exists. If this journey brought you a moment of peace, consider letting others find their way here too. A like, a subscription, a quiet word to someone who might need rest. Each small act helps this community grow, one sleepy soul at a time. There are more wonders waiting in future journeys, more mysteries to drift through when sleep feels far away. Right now, as you lie here in the stillness, the invisible universe continues its quiet work. Dark matter holds galaxies together in its gentle grip. Dark energy pushes the cosmos ever outward. And you, made of ordinary matter, that rare and precious minority, rest peacefully within the embrace of forces you cannot see. You are part of this vast, invisible architecture, a small bright point of awareness in the cosmic dark. Let your breath become slow and steady, like the expansion of space itself. If your eyes feel heavy, let them close. Let your shoulders release any tension they still hold. Allow the weight of your body to sink into wherever you are resting, trusting that you are safe, that you are held by the same gravity that shapes the galaxies. There is nothing more you need to do tonight. Tonight, as you rest, the dark matter around you continues to hold the Milky Way in its invisible embrace. The dark energy between galaxies continues to stretch the fabric of space. The particles that may make up the darkness continue their undetected passage through everything, including you. Life carries on in realms we cannot see while you sleep. You are a small, bright presence within this vast, dark universe, peacefully resting among the invisible wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that most of the universe is still waiting to be understood, and that there is something peaceful in not knowing everything. This has been Drowsy Discovery. Good night.